Walk into your house on an August afternoon and the heat hits you like a wall you didn't know was there. The air conditioner is running. You can hear it. You can feel the cold air sliding out of the vents. And yet, the rooms upstairs stay stubbornly, suffocatingly warm, like the house is sweating from the inside. You crank the thermostat down 2 more degrees. The compressor groans. The bill climbs. And somewhere above your head, in a space you almost never go, the real problem is sitting there, cooking quietly in the dark. That space is your attic. And on a clear summer day, it can reach 150 degrees. Not the outside, the inside of your roof. A sealed oven sitting directly on top of your bedrooms, radiating heat downward through the ceiling all day, and most of the night, fighting your air conditioner with every degree it gains. And here's the strange part. The cure for this used to be everywhere. You could drive through any town in America 50 years ago and see them spinning on rooftops, little metal mushrooms turning lazily in the breeze. They were on farms, on factories, on warehouses, on ordinary suburban houses. And then, almost without anyone noticing, they vanished. They're called turbine ventilators, whirlybirds if you grew up around them. And the claim attached to them sounds almost too good to be true. No motor, no wiring, no electricity at all. Just a spinning aluminum head that, according to field testing, can pull peak attic temperatures down by as much as 37 degrees and trim cooling costs somewhere in the neighborhood of 15%. A device that costs less than a tank of gas and runs on nothing but moving air. So if it worked that well, why did we abandon it? And should we be putting them back? Let's actually figure that out. The dream behind the whirlybird is older than the whirlybird itself. The idea that you could move air through a building without burning a single thing to do it is one of the oldest tricks in architecture. The Persians figured it out centuries ago with tall masonry wind catchers that funneled desert breeze down into the cool lower rooms of a house and pushed the hot, stale air up and out the top. They had no fans, no fuel, no power. They had geometry and wind, and that was enough. Across the ancient world, builders treated the way a structure breathed as seriously as they treated the way it stood up. A building that couldn't breathe was a building that made you sick. For a long time, that was the limit. You shaped the building, and you hoped the wind cooperated. The push to do something more aggressive came with industry, with deep mines that needed fresh air pumped down to keep men alive, and with hospitals where stagnant air was understood, correctly, to be a killer. Engineers built furnace-driven systems and steam-powered fans, machines that worked but demanded fuel and maintenance and constant attention. They moved air, but they were never free. The breakthrough, when it came in the early 20th century, was almost insultingly simple. Take everything those steam engines and furnaces were doing and let the wind do it for nothing. The turbine ventilator was a spinning cowl that sat on the roof and quietly dragged the hot air out of the space below it, with no motor, no fuel, and no human touching it ever again. You bolted it on and you walked away. And here's the part that gets overlooked. It wasn't relying on one clever trick. It was stacking 3 of them on top of each other. The first is Bernoulli's principle, the same physics that lets an airplane wing lift 100 tons off a runway. As wind sweeps across the curved vanes of the turbine head, the air is forced to speed up. And when air speeds up, its pressure drops. That drop creates a little zone of low pressure inside the turbine, a vacuum, and that vacuum reaches down into your attic and pulls the hot air up and out. A plain static vent just sits there, hoping heat drifts away on its own. The turbine takes the kinetic energy of the wind and uses it as a pump. The harder the wind blows, the harder it works. That's the elegant part. But wind doesn't always blow. And this is where people assume the thing just stops. It doesn't, because it also rides what engineers call the stack effect. And you already understand it, even if you've never heard the name. Hot air rises. It's less dense than cool air, so it floats. In a properly built house, with vents tucked under the eaves and a turbine sitting at the peak, that rising warm air sets up a gentle, constant current. Cool coming in down at the edges, hot going out the top. The turbine becomes the chimney that current wants to escape through. On a dead still day, when the head isn't even turning, the house is still breathing. And the third trick, the Venturi effect, sharpens the other 2. As air squeezes through the narrow gaps between the spinning vanes, it accelerates. The pressure drops again, and the exhaust pulls harder. 3 principles, all compounding, all pointed at one job. Generate a steady suction at the highest point of the building and yank the heat out before it has a chance to sink back down into your living room. Does it actually deliver? Mostly, yes, with caveats that matter. Field studies on attic ventilation have found that adding turbine units can raise the rate of air exchange in a roof space meaningfully over the course of a year, with the biggest gains coming when the wind hits the unit straight on. The headline number, that drop of around 37 degrees in peak attic temperature, comes out of warm climate testing, and the energy savings that follow land in the rough range of 15% off a cooling bill. Consider what that means. The Department of Energy figures that every single degree your attic heats up can push your cooling load up by as much as 4%. Strip 30 degrees out of that attic, and you are no longer paying to fight a furnace bolted to the top of your house. A standard 12-inch turbine can move somewhere between 250 and 350 cubic feet of air a minute in a light breeze. A 14-inch unit moves more, and every cubic foot of that is free because the thing burns nothing. So with all of that going for it, here comes the honest part, the reasons it disappeared. The first is the simplest. One turbine is usually not enough. Research has shown that a lone 12-inch unit working away on a typical roof can leave the air inside that attic moving at less than half a foot per second, which is so slow that ventilation engineers technically call it still air. The device works. It just gets badly outmatched by the heat load of a big modern house with a dark roof. You need to size it correctly, and most builders never bothered. The rule of thumb is roughly 1 square foot of ventilation for every 300 square feet of attic floor. And in a brutal climate like the Gulf Coast, you want to double that. People bolted on a single turbine, watched it underperform, and decided the whole concept was a gimmick. Then there's the part everyone who grew up near one remembers, the squeak. The defining feature of the turbine, that spinning head, is also its weakest point. The bearings wear out, moisture gets in, dust gets in, the lubrication dries up, and one quiet night, the thing starts to grind and whine, and that sound travels straight down through the rafters into the bedroom directly below. Cheap units did this fast, and a device that wakes you up at 2 in the morning earns a reputation it never fully shakes. There's a subtler failure too, called short-circuiting. Put a turbine and a ridge vent on the same roof, over the same attic, and the turbine, pulling hard, can actually reverse the ridge vent, sucking outside air in instead of pushing hot air out, dragging rain and snow in with it. So roofers learned to pick one exhaust system and commit. And since a ridge vent is easier to install and hides under the shingles, the turbine was usually the one that got cut. Which brings us to the quiet, unglamorous reason these things really died. They're ugly, or at least somebody decided they were. A turbine sticks up off your roof and spins where the whole street can see it. A ridge vent is invisible from the ground. In a country where curb appeal moves money, that mattered. Homeowners associations started restricting them, sometimes banning them outright, sometimes allowing them only on the back slope of the roof, which is frequently the wrong side for the wind and cripples the whole point. Meanwhile, building codes tightened. As houses got sealed up tighter and more efficient, codes began demanding mechanical ventilation systems that guarantee an exact, controllable rate of air exchange. A passive turbine, whose output rises and falls with the weather, simply doesn't fit in a spreadsheet. It fell into a regulatory blind spot and stayed there. Nobody disproved it, it just stopped checking the right boxes. So should you put one back on your roof? The truthful answer is, it depends on where you live and what you're chasing. If you're in a hot, windy place, the Southwest, the Sun Belt, anywhere the breeze actually shows up, a properly sized pair of turbines is still one of the cheapest ways on Earth to take the load off your air conditioner. The hardware on a 12-inch unit runs somewhere between $20 and $100. Installation adds a few hundred per unit, depending on your roof. For a typical attic, 2 of them, sized right and placed where the wind hits them, can pay for themselves in a handful of summers, and as a bonus, they keep your shingles cooler and your roof deck drier, which buys you years of roof life you'd otherwise have lost. But be honest about the other side. In a cold climate, attic moisture can freeze the vanes solid in winter, shutting the thing down exactly when you don't want a hole in your roof. And in a tight, modern, high-performance house where a mechanical system is already carefully managing every cubic foot of air exchange, punching an uncontrolled passive exhaust into the envelope can throw off the pressure balance the whole system was engineered around. For a lot of people building new today, a full-length ridge vent is the smarter pick. It runs the entire peak of the roof, ventilates evenly instead of in 2 hot-spotted points, and has nothing to wear out, nothing to squeak, and nothing to draw a letter from the homeowners association. What's worth sitting with, though, isn't really the verdict, it's the pattern. We had a device that ran on the wind, cost almost nothing, and lasted for decades, and we set it aside mostly because it was loud when it was cheap, ugly when it was visible, and hard to fit on a regulator's form. None of those are the same thing as not working. The physics never stopped being true. The wind never stopped blowing. We just decided, quietly, building code by building code and bylaw by bylaw, that a thing which works for free is somehow less serious than a thing you pay to run. Think about that. Think about it the next time your meter is spinning faster than any whirlybird ever did. If learning how the simple, forgotten machines actually beat the expensive ones is the kind of thing you came here for, then subscribing is the easiest way to make sure this knowledge keeps surfacing instead of getting buried again. And if you want to see how this exact same idea, hot air rising and pulling cool air up behind it, can be scaled up to cool an entire house with no electricity at all, then the video you want next is the one on the solar chimney. Go watch that one right now.